Hello learners, welcome to this tutorial on reinforcement learning and its usage in robot exploration. So first let us discuss about an introduction about machine learning. So a machine learning is a subset of an artificial intelligence system. So we will be writing an algorithm where its performance will be improved as it is exposed to more and more data. As the number of data given to a machine increases, it learns and its experience gets improved. So thereby in the near future, if it comes with some input, it can able to make a right prediction. So a major subset of your machine learning is deep learning system, where we will be using your neural networks to do the predictions. So here in machine learning, we have three major types. One is supervised learning, unsupervised learning, and reinforcement learning. So the topic of discussion in this tutorial is on the reinforcement learning. So first let me give some introduction about the supervised learning, unsupervised learning, and reinforcement learning, and how it is different from each other. So let us try to understand. So in case of a supervised learning, we have a data set with the ground truth values. So each and every data is associated with a label or the ground truth value. So using this, we can determine the relationship between the input and the output. So a relationship between the input and output can be obtained if I know a data with its ground truth value. So here the type of data which we work on in supervised learning is labeled data. So each and every data should have a label. And the type of problems which we can solve using the supervised learning is classification problem, which is nothing but categorizing into classes, and regression problem. So predicting a real-time output. So in this approach, we map the labeled inputs to the known outputs. And it is a direct feedback system. The algorithms in supervised learning are linear regression, logistic regression, support vector machine, k nearest neighbor, random forest, etc. So the applications where the supervised learning used are risk evaluation and in forecast sales. Next type of learning is your unsupervised learning. So in unsupervised learning, we have the data, but the corresponding ground truth values or labels are not present. So in such scenario, we can find the association or patterns in the given data. We can find some relationship between the data or association between the data. So here the type of data which we use is unlabeled data, and the type of problems it can solve is association problem, and we can do data clustering based upon some characteristics. So here the approach used is understand the patterns and discovers the output. And this is a no feedback system because we don't know the ground truth value, so we can't correct our machine if it makes a wrong prediction. So in case of unsupervised learning, the algorithm, some of the algorithms are k-means, c-means, a priori, etc. And mainly it is used in your recommendation system and in anomaly detection system. And the third type of learning is your reinforcement learning. So this is completely different from your supervised and unsupervised learning. So in supervised and unsupervised learning, we require the data. In case of a supervised learning, we require both data and the labels. In case of a unsupervised learning, we should have a data to train the machine. Whereas in a reinforcement learning, the learning takes place without any initial data. So where an agent interacts with the unknown environment, by doing so, it gains the knowledge or experience through its actions. So by performing an action in an environment, the knowledge is gained or the experience is gained. So we don't start with an initial training process. So we try to explore in the environment by taking some actions. So the agent's action, it comes with a penalty or a reward. So each action taken by the agent in an environment comes with a reward or a penalty. So if the decision is right, if the action is correct, then it will be given with a reward, and if the action is wrong or it is not pertaining the agent to go to its destination or the final goal, then it will be given with the penalty. So the main aim of this reinforcement learning is we should maximize the reward. So we should find the sequence of actions which will result in the agent to reach the final goal. So here in reinforcement learning, the type of data is no predefined data, and it is a reward based problem. So each action comes with a reward or penalty. So the sequence of operation performed by the agent should be obtaining a reward, which means it is trying to reach the goal in a better form. So the approach followed here is trial and error method, and the feedback mechanism is reward based action will be taken. So here we have multiple algorithms like Q-learning algorithm, SARSA algorithm, and the applications used is in self-driving cars and in gamings. We try to make use of this reinforcement learning. So now let us discuss about this reinforcement learning in detail, and also I will show you a case study of how to use this reinforcement learning for robot exploration in an unknown environment. So first, let us start with the introduction of a reinforcement learning. It is a feedback-based machine learning technique. It gets the feedback based upon the action performed by the agent. So for example, let us take an agent which is a robot. It is put onto an environment which is not familiar to that robot, right? So it is going to do some actions in that unknown environment. Based upon its action, whether it is going to reach the final destination or not, it will be given with a reward or a penalty. So for each good action, the agent gets positive feedback called as reward. For each bad action, the agent gets a negative feedback or penalty. So our primary goal is to improve the performance by getting maximum positive rewards. So we try to find the sequence of steps taken by the agent. In our case, it is a robot, right? So robot performs certain action in an environment. We need to find the sequence of action, and whether that sequence of action results in reaching the destination or not. If it reaches the destination, then it is given with a positive reward. If the sequence of action results the robot in meeting with some obstacle, then in that case it will be given with a penalty. So here we take an agent, put it onto an environment. So currently it is in some state. So that state is called as ST. So now the agent does some action. Okay, so we will have certain set of actions, and the agent has to pick the right action. So how this right action is picked is called as a policy of an agent. So it is a strategy of an agent to decide which action will be more suitable to be performed in an environment. So it performs certain action, that is AT. So what happens? The environment provides the feedback to the agent depending upon the action performed by it. So that is nothing but the new state of the agent, and in the new state, if it performs an action, what will be the reward? So what type of action should be performed in the new state? So that will be given by the RT plus 1. So it is completely a feedback based mechanism system. So agent performs an action in an environment, and based upon the action, a state of the agent will be changed, and also what action it should perform in the next state will also be determined. So we need to know certain terms to have a better understanding about reinforcement learning. So where we call the agent is nothing but the entity which performs action in an environment to get some reward. So in our case, we are going to consider a robot put onto an unknown environment. So robot is our entity or the agent. So the environment is nothing but the condition which an agent has to face. So we are putting the robot in an unknown environment, right? So some obstacles or something is going to be there in the environment. So that is the scenario which the agent needs to face. So that is called as an environment. So there will be a reward, an immediate return given to the agent whenever it performs the correct action or task. So it is given immediately. Once the agent does some action, a reward will be given. Either the reward can be positive or it can be a negative. So negative in the sense we take it as a penalty. It's an immediate return. State refers to the current situation written by the environment. So what is the current state of the agent in the environment? That is given by the state. Policy. So policy is the agent right now it is in a current state. Agent is in a state, right? It has to do some action. On what basis it is going to pick that action? That is called as a policy. So it is a strategy applied by the agent to decide the next action. Okay, it is the strategy applied by the agent to decide the next action based upon the current state. Value. It is something similar to that of reward. So reward is for each action. For each action we will get a reward. Right? Whereas a value is something like a long-term return with some discount. Okay? If I perform certain sequence of operation, whether it will make the robot to reach the destination or not. So it is something like a long-term. Okay? If I do certain steps, if I take some certain actions, whether the robot or agent will reach the destination or the final goal. That is given by the value. Okay, it's a long-term return with a discounted value. And we have a Q value. So Q value is similar to that of value. Only one thing is, it also takes into account the current action. Okay, for a particular action, what will be the value, Q value? Right? What will be the scenario for which it has to take a particular action? So these are some of the terms associated with your reinforcement learning. So we have different types of reinforcement learnings like value-based reinforcement learning, policy-based reinforcement learning, and model-based reinforcement learning. Value-based in the sense our algorithm, reinforcement learning algorithm should work in maximizing this value function. So value we already know. Value is nothing but the long-term expected outcome. If I perform certain sequence of operation, whether the agent can go to the final destination or not. Right? So it's a long-term based output. So we need to maximize this value. How much chance we have if an agent tries to reach the destination in a long-term basis. Right? So here the value function needs to be maximized. So the agent is expecting a long-term return of the current states under a particular policy. By taking certain actions, it is expecting that it is going to reach the destination often. Second one is policy based. It is the action based. Right? First one is we need to see whether our action results in a higher value or not. Whereas in the second algorithm, it is policy based. So what type of action should be performed so that the agent reaches the destination or the agent gets a maximum reward. So a policy needs to be formulated such that the action performed in every state will result in attaining maximum reward in the future. Okay. So a policy, so different policies, different actions will give me different value and reward functions. So we have to select the appropriate policy so that we get maximum reward. And the third one is model based. Model based is something similar to that of a mathematical modeling. So we can create a mathematical model of agent in an environment and we try to see how the agent interacts with the environment by solving some mathematical equations. So there are two main policies. So policies, as I said, strategies applied by the learning agent of picking up the action. So how the action will be picked by the agent to be performed in an environment. So we have two policies. One is on policy, another one is off policy. So on policy is something like when the agent does some action, it gets a reward or penalty. So a Q table will be formed using the current action. Okay, so for each and every action will result in a reward or penalty. So those data will be recorded. For each step, it will be recorded. Then in the future, we will be using the same Q table for picking the appropriate action. That is called as on policy. So first, the agent tries to traverse in an environment. In different directions, it tries to move. It tries to find which is the action to be performed. So a Q table will be updated. So after updating the Q table, we will try to make use of the Q table to do the next action performed by the agent. That is on policy. So the agent learns the value function according to the current action derived from the policy. Right? So from using some strategy, it forms a Q table. Then from the Q table, it finds the appropriate action to be performed in the near future. So one such technique is a SARSA technique. So SARSA is state, action, reward, state, action. Right? Yes, first S stands for state, that is current state. In the current state, the agent performs an action, it gets some reward, and it moves into the next state, and in the next state, it performs some action. Right? So that is SARSA technique. This is a on policy technique. So whatever the experience it gains earlier, that experience will be used for deciding the current action. Second type of policy is off policy. So off policy right now, what it is going to do? It is not going to take the decision based upon the current strategy. Right? So it is going to take the decision based upon some other strategy. Okay? So some other strategy might be incorporated and the Q table might have been updated, and depending upon the Q table content, the data can be utilized here. So such a policy is called as off policy. So the agent learns the value function according to the action derived from another policy. Okay? Another way of determining the action. So based upon that, a Q table will be there. From the Q table, the details will be taken. The values will be taken for selecting the appropriate action. So here we try to use a Q learning technique, which is a greedy approach to learn the Q table. For example, let us take in an environment, we are putting the robot for the first time. Okay, so there will not be any Q table right now. Okay, so first I have to pick. For example, let us take the robot can move in 4 directions: north, south, west, east. It can move in 4 directions. So in which direction it has to go? Whether it has to go in north direction, south direction, west direction, or east direction, it does not know, because it does not have any Q table right now. So it needs to do some random action. It needs to pick some random direction. So it can go in west direction. Okay, it can take the first step in the west direction. So if that west direction is one of the sequence in the final destination path, then it will get some weightage, a reward. Not reward, so it will be something like a small value will be given. So for every step, a value will be assigned. Whether the continuous values will result in a positive reward or negative reward, we will know only after the exploration process. Because whether that step will result the robot in reaching the destination or not, we don't know right now. Right? So it can be decided only after many steps, whether it can reach the destination or not, depending upon which a Q table will be formed. So by doing some random actions in an environment by the agent, a Q table will be formed. So this is called as a off-policy reinforcement learning. So now let us discuss about SARSA algorithm, which is a on policy. So on policy means already I have a Q table, right? I have a Q table and we are going to select the best action from the Q table, right? So SARSA means, as I said, state, action, reward, state, action. So the first state is the current state. In the current state, the agent performs an action. So it will get a reward. So the agent goes into the next state. In the next state, what action it has to perform, right? So that is this SARSA algorithm. So the maximum reward for the next state is not necessarily used while updating the Q values. It depends upon the action of your agent. So a new action and reward is selected using the same policy, right? So first we need to explore by using Q learning technique. We get the Q table, then use that Q table for our SARSA algorithm. So how this Q values will be updated in the sense, it depends upon the current state of the agent, which is S1. The action the agent chooses, that is A1. It gets some reward for that particular action. Then the agent moves into the next state, S2, and in the next state, what action it has to perform. So all these things will be considered while updating a Q value. So current state, current action, whether it has got a reward or not, next state and the next state action. So everything will be considered while updating the Q table value. So some of the hyperparameters in the SARSA algorithm are learning rate, which is determined by alpha. So what is learning rate? How fast we try to learn, how fast the algorithm tries to learn. It determines to what extent the newly acquired information overrides the old information. For example, if the learning rate is 0, the agent does not learn. It does not update its parameters. Whereas if it is 1, the agent considers only the most recent information. So we should have a value in between 0 and 1 so that it takes the current information and also its past information so that it can give a better predicted value. Then the second parameter is a discount factor, which is also called as gamma. So it determines the importance for the future rewards. Okay, whether my future rewards are important or not. That will be determined by this discount factor. So 0 means it makes the agent to be opportunistic, whereas 1 means it will make the agent to get long-term high rewards. And the initial condition of the Q values, Q table. So Q table entry will be depending upon the current state and the current action. S0 and A0. S0 is the state, A0 is the action. For each state and an action, a Q table entry will be there, right? So we need to initialize this Q table entry initially, right? So usually we put a low value there in the Q table entries, which makes our algorithm to be exploratory in nature. So we need to explore all the possible conditions, then come to a conclusion, okay, which will be the right action to be taken by the agent. Next one is Q learning. As I said, when the robot comes into the environment for the first time, it does not have any Q table entries, right? It has to learn from itself. So it has to do some random actions. It has to perform some random actions. Based upon that random action, the Q table values will be determined, right? So such a technique is called as Q learning technique, where this Q stands for quality. It represents how useful a given action is in gaining some future rewards. So it is an off-policy reinforcement learning algorithm that seeks to find the best action to take given the current state. It is considered off policy because the Q learning function learns from actions that are outside the current policy, because it is the actions are not determined from the Q table. We are doing some random actions, right? So it is not from the current policy. It is from the random action. So that is why it is called as a off policy. When Q learning is performed, a Q table or Q matrix will be created, and this Q table can be used by the Sarsa algorithm to do further exploration. And the shape of the Q table will be, each entry will be associated with the state and the action, and initially it will be assigned to zeros. So Q values are updated and stored after an episode. So episode is something like a sequence of operation, right? So an agent performs a sequence of operation. It might reach a destination, that is called as one episode, or a sequence of operation might result in an agent colliding with an obstacle, that is also called as an episode. So a sequence of steps made by the agent, whether to reach a destination or an obstacle, is called as an episode. So for every episode, for every sequence of operation, the Q values will be updated. So this Q table becomes the reference table for the agent to select the best action in the future. So first we will use a Q learning technique to create a Q table. Then use this Q table with the help of a Sarsa algorithm to make the appropriate actions to be performed by the agent. So now let us talk about the case study, the programming part, which we are going to discuss in this tutorial. So here I am going to first create an environment. So this is an environment which I am going to create, where I have 9 columns and 9 rows. 9 columns and 9 rows. So we take it as each cell. Each cell is going to have 40 pixels. Right? Each cell is going to have 40 pixels. So the total dimension of the environment is 360 pixels by 360 pixels. Right? So we create an environment, and we put some obstacles onto this environment, like a building, bank, street crossing, trees, traffic lights, etc. We put some obstacles here, and then we also put the agent in some location. So I am going to put the agent in this first box, right? And we need to specify the destination point also in the environment. So I put a flag here. Okay? So this will be our destination point. So our robot should find the shortest path from its current position to reach the destination. It needs to find the shortest path. So it will do that by doing the exploration of the environment. It will try to explore the environment, thereby it tries to find the shortest path to the destination. So that we are going to create an environment, and we are going to implement the reinforcement learning in this environment for the agent to find the shortest path to reach the destination. So what is the steps involved here? First we import all the necessary packages, create an environment, get the initial observation. Get the initial observation in the sense, currently the robot is where? In what position? What is the state of the robot? Then from that you choose an action. We might have different actions. For example, a robot at this position, it can go down or it can go towards right. Whereas if a robot is in this some other position, right? If it is in this position, it can go up, down, left or right, right? So it has to pick the appropriate action. Okay, so we try to choose an action and see whether the agent has collided with an obstacle or not. If it has collided, then one episode is completed, right? So it goes to the initial observation. It goes to the initial stage. If it is not collided with the obstacle, then it gets some reward for this action. Right? It gets some reward for the action. And then it goes into the next state. It goes into the next state. So again in the next state, it has to choose an action. Okay, in the next state, it has to choose an action. So it selects an action. and we will check whether it collides with an obstacle. If it collides with an obstacle, again an episode completes. We perform certain sequence of operation and it has not yielded our robot to reach the destination. So the episode completes there. So once it collides with an obstacle, we go back to the initial position again. If it has not collided with the obstacle, in that case we are going to check whether it has reached the destination. So destination is our flag. We will check whether it has reached the destination or not. If it has reached the destination, then we will stop at that point, right? So that completes one episode, and the reward will be positive, +1. Whenever the agent collides with an obstacle, the reward will be -1, right? It's a penalty. Whenever the agent comes to contact with the destination, then the reward will be +1. Any boxes in between the agent moves, we will get a reward between +1 and -1. If it has not reached the destination, then again I go back to the previous step in the sense next state, and there again I try to perform an action. So this continues until the robot tries to find the destination. So once the robot finds a destination, it will not stop there. It will try to find the alternate paths also. Okay, it will try to compute all the possible paths. Then from all the possible paths, it will try to determine which is the shortest path. Then that shortest path will be used in the future. So it will be easy for the robot in the future because it has all the knowledge. It knows what are all the different ways in which it can reach the destination. So it has a complete idea. So thereby what it can do in the near future, it can take the appropriate path and it can move to the destination in a faster way. So this is the program which we are going to discuss right now in this tutorial. So we create an environment with obstacles, agent position and destination here. So here I have put an agent and we will put a destination at some location in the environment. Then here we are going to implement both Q-learning technique as well as a SARS algorithm. So initial exploration will take place with the help of a Q-learning technique. So to determine that, we take a parameter called as epsilon. So epsilon is a greedy value. So I am going to take an epsilon. So for 90%, if my epsilon is greater than 90%, we can set any value. If it is greater than 90%, I am going to do an Q table based updation. If the epsilon is less than the 90%, then I am going to take random action. So the random action selection will be done by our Q-learning technique, and the best action will be selected based upon the SARS algorithm, right? So Q-learning technique will be implemented when I have epsilon less than threshold. So threshold I am going to set it as 90%, right? If my epsilon is less than 90%, then we are going to take a random action. If my epsilon is greater than 90%, then we are going to take the best action from the Q table. So depending upon this action, our agent location in the environment will get updated. Then for a particular action, up, down, left or right, it will get a reward or penalty. And based upon this, a Q table will be updated. So agent position in the environment gets updated. Then we try to check whether the agent has reached the destination or not. If it has reached the destination, then again it goes to the initial position. It tries to find the alternate path of reaching the destination. If not, it goes to the updated location, and then again depending upon the epsilon value, a Q-learning technique or SARS technique will be selected and reward and Q table updation will take place. So this procedure will carry on again and again. So this is what we do in our program. So now let us go into our program. So I am going to open a Jupyter Notebook. So in Jupyter Notebook, I am going to do this program. So first we start with the necessary packages, importing the necessary packages. So NumPy is for performing matrix computations. Tkinter is used for building the GUI. So we need to build an environment. For that we will be making use of this Tkinter package. Time package will be used for seeing our robot movement in the environment. Right? So we need to visualize the robot movement, how it is moving, how it is traversing towards the destination. So for that we will be making use of this time package. Then from PIL we import the image because we need to put some obstacles onto our environment. So I am going to use this package for putting the obstacle onto the environment. Then pandas is a data analysis or manipulation tool which we will use in our program. Then matplotlib as the pyplot, which will be using it for plotting mainly episode versus cost function, episode versus step function. We try to plot it there. And system is for system specific parameters and functions. So we import the necessary packages. To execute each and every cell in the Jupyter Notebook, we need to press Shift Enter. Right? So right now the first cell is executed. So now let us go to the second cell. So in the second cell, I am going to define the size of the environment. Right? As I said, our environment height is going to be 9. Environment width is going to be 9. Right? So 9 rows and 9 columns. So in each row and each column, I am going to have 40 pixels. So in one box, I am going to have 40 pixels. Okay, 40 pixels per box. So then we define a variable A to save our final route. Okay, so our robot traverses in the environment and it finds the shortest path finally. Right? So the shortest path we need to save in some variable. So for that I am going to make use of this A variable. So now we will start building our environment. So I am going to define a function to build the environment. Right? So I am going to use the TK package. In that we have a function called as canvas function. So using this canvas function, we try to create a canvas which is a background environment. So I am going to use a white color background. So what should be the size of the background? Which is nothing but environment height into pixels. So environment height is 9. So 9 into 40, it will be 360. Same way width. Width is environment width into pixels, which is 9 into 40, again it is 360. So we create an environment of 360 by 360. 360 by 360. So now once I have created the environment, I am going to put the grid lines. Okay, we need to put the grid lines differentiating row and columns. So for that I use this for loop. Okay. So here I take a for loop, first for loop, which varies from 0 to environment width into pixels. Right. So environment width we know 9 into 40. So 9 into 40 in the sense it is 360. So our column value varies from 0 to 360 with an incrementation of 40. Right? So it takes a value 0, 40, 80, 120, 160. So like that it goes on till 320. Right? The final value will not be included. 360 will not be included. So our column takes a value 0, 40, 80, 120, 160, 200, 240, 280 and 320. And use this column values to create the points x0, y0 and x1, y1. Right? So we are trying to create 2 points, 0 point and 1 point, which has x coordinate and y coordinate. So x0, y0 is 1 point, x1, y1 is another point. Right? So first x0, y0 is nothing but column. So first initially when the for loop runs for the first time, it will be 0. 0, 0 and 0, environment height into pixels, which means environment height is column is 0, height is 9 into 40, which is 360. So 0, 360. So my points are 0, 0 and 0, 360. Which means in our environment, so 0. So the first value represents width, right? First value represents width, second value represents height. Okay, width, height. So 0, 0. So 0, 0 is this position, right? 0, 0. Then I have 0, 360. So 0, 360 is this one, this point. Right? 0, 0, 0, 360. So we draw a line. Same way, next position, what I am going to do, this is going to be 40, right? So 40, 0, 40, 0 and 40, 360. So that will draw the second line. Next one is 80, 360, 120, 360, 160, 360. So like that it goes on. So we draw all the column lines, all the grid lines. Same way we do it for the row. So row, we take first the width value, right? Width is 0, 0, 40, right? So this point 0, 40. Then this point is 0, 360, 40. 0, 40 and 360, 40. Right? We draw a line. Next one is 0, 80, 360, 80. 0, 120 and 360, 120. So like that we define the points and we try to draw the horizontal lines. So that is what we do here in this two for loops. So column is for getting the grid lines along y-axis or the width axis. Row is used for creating the row lines. Once this is done, we have created the grid. We need to define the objects, obstacles. So for that, I am going to use image.open. I have some images of the road closed, trees, buildings. I have some JPEG images. So I try to take those images into a variable and create an object out of it. Okay, for each obstacle, I am going to create an object. Then we will be using this object in our environment to place the obstacle. Right? So road closed, tree 2, building 1, building 2. So like that, I have multiple obstacles defined and we create the corresponding objects for that obstacles. So same way, once I have created the objects, I need to place these objects in our environment. We need to place this object in our environment. So for that, what I do, I use this canvas widget.create_image function. So there I try to put the location. So pixels into 3, which is 40 into 3. So 40 into 3 is 120. Same way 40 into 4 is 160. So 120, 160. I am going to put an object. What is the object? Which is obstacle 2. So obstacle 2 is nothing but the tree image. Right? So tree image, I am going to put it onto 120, 160. So remember, the first one will be width, second one will be height. Okay, we are putting the obstacle in this 120, 160, width, height information. And in that box, I am going to put that obstacle in the northwest direction. So we can put in northwest, southwest, so we have different directions. I am going to put that obstacle in the northwest direction. Same way we put all the obstacles. Okay, all the obstacles in our environment. Okay, all the obstacles, I am trying to put it into width position, height position. So then I am trying to create an object for our destination. So destination is, I am going to use the flag image, right? For that flag image, I create an object and I am going to use that object. I need to place it onto our environment. So I use this width and this height. So this is 40 into 6 is 240. Same way 240, 240, I am going to place the flag, which will be our destination for the robot. Same way, I take a robot image, create an object for that robot image, put that robot image in this location, 0, 0, I am going to put our robot, right? And pack all the objects. So we created an environment. So we created an environment. In that environment, we have put all the obstacles, robot, as well as the destination flag. So everything is updated here. So let me run this cell. We will go to the next function. So we need to define certain functions like resetting. So resetting means whenever an episode is completed, right? The episode is nothing but sequence of steps, right? So the robot performs certain actions. If it encounters with an obstacle or a destination flag, an episode is completed, right? After completing this episode, it has to come back to the original position. It has to come back to the initial state. For that, we define this function, right? Once an episode completes, the robot needs to come to an initial state. So for that, we define this function, reset. So first, we delete the agent in our environment. Okay, we delete the agent. Then I am going to put our agent in the initial position 0, 0. Okay, it comes to the initial position. Okay, so after taking a certain steps, it might be in different position in the environment, right? Once the episode is completed, I need to come back to the initial position. So I am trying to clear that updated position and I am trying to go back to the initial position. Right? So that is done here. Then we define certain dictionaries like D. So this D will be used for storing the sequence of operation. Okay. So like that, the dictionary will be updated for every sequence of operation. For every episode, the D value will be updated. So if it comes with the destination, if the agent reaches the destination, then that sequence of operation will be stored. If the agent encounters an obstacle, the sequence of operation will not be stored. Only those sequence will be used for providing penalty for the sequence of operation. Right? So we try to initialize or clear the dictionary D. Okay? Current sequence of operation, we try to clear it. And the corresponding index of the dictionary also, it is initialized to 0. And we return with the agent position. So the next function which we are going to talk about is taking action. Okay, in the current state, a agent needs to pick an action, right? It can pick an action something like up, down, right or left. We have 4 options. So we need to define that function. So here the function is defined as step. So in that first I am going to get the robot's current coordinates. Okay. Right now in the environment, where is the robot? That current coordinate I am going to take. Then we take a variable base action. We initialize this base action with 0, 0. Okay, initially I am going to put it as 0, 0. So I take the current state of the robot and I take the base action. Right now it is initialized to 0, 0. So now in this if statement, I have 4 operations. One is up, down, right and left. Right. So up means I am going to use 0, down means 1, right means 2, left means 3. I am going to see whether my action is 0. Whether my action is 0, which means whether I need to move to up or not. Whether the robot is going to select up or not. If it is up, if the action is up, I need to check the state of 1. So where the 1 represents the height information, 0 represents the width information, right? 1 means height, 0 means width, right? I am checking whether my state of 1 in the sense whether my state along height direction, whether it is greater than or equal to pixels, whether it is greater than or equal to 40 pixels, I am going to check. If it is greater than or equal to 40, then only I can move up. Otherwise, it will come out of the environment, right? So first, I am checking my state, okay? Whether my state along height direction, whether it is greater than 40 pixels or not. If it is greater than 40 pixels, then I can perform an action. What action I will be performing? We will decrement the pixels by 40. We will decrement the pixels by 40, thereby I go up. Okay. So in order to go up, I need to decrement the pixels. In order to go down, I have to increment the pixels, right, along height direction. Right. So pixels will be decremented for performing to move along up direction. Pixels will be incremented to perform an action to move towards down. Same way, in case of a right and left, what we do, we need to take width. The width pixels will be incremented so that I move towards right. It will be decremented to move towards left. So that is what we do here. So we take the base action 1. So 1 is nothing but the height. Along the height, I am going to decrement the pixels, which is 40. 40 pixels I am going to decrement. So I am going to take 1 step up. In case of a down, what we do? We increment the pixels, right? This is the difference. In up, we decrement the pixels. In down, we increment the pixels. Which one? Height pixels. Along the direction of height, we try to do this. Same way in action 2, right and left operation, what we do? We increment or decrement the pixels along width direction. 0 means width, right? Along width direction, I am going to increment the pixel if it is a right operation. If I am going to decrement the pixels if it is left, right? So this is what we do when we have an action up, down, left or right. Right? So this is required for updating our robot position in the environment. So depending upon this state and action, we try to update the canvas. So our agent moves to a new width and new height. Okay, it goes to a new width and new height. And the corresponding coordinates is obtained. The agent's coordinate is obtained and it is put onto the D. So D is our step movement. Okay, so step movement or the sequence of operation is stored in D. Right? Then this we are going to take it as the next state. Right? The updated sequence we are going to take it as next state and the index value is also updated. Right? So now I have taken the first step. Next state we have obtained. So we need to check whether this next state is a flag or not. Okay? If it is a flag, which means we have reached the destination. Okay? We have performed one step, one operation. I need to check whether it is a flag. If it is a flag, then one episode completes. And our goal is achieved, which means I can give a reward of 1. So done flag, I am setting it to true and the next state is, we say it as goal as reached. If it is not, okay, if the next state is not equal to flag, in that case, I am going to have subsequent steps, right? So this is only the first step. I will be having subsequent steps. So for that, if it is for the initial first time I am doing that sequence of operation, we define a variable called as C. We specify it as true. So this is a dictionary for updating the sequence of steps for the first time. So I take the length of the D, put it onto my F. So F is the final sequence of operation, which will be a shortest path towards the destination. So D is the current sequence of operation, F is the final. Okay, so like D, we will get multiple sequence of operation of reaching the destination, right? So from this operations, we need to select the final destination path. So that will be uploaded in the F. Right? So once I put the sequence of operation here, I set this initial sequence of operation I have set, so I have set it to false. Then we need to see whether this sequence of operation is shortest or longest. So this is the first time which we have traversed. So we have only one sequence, so we put the sequence to both long and short. If it is for subsequent operation, right? If the sequence is repeated again for the second time or third time or fourth time, in that case, what happens? I am going to check the current sequence of operation, whether it is less than the final path. Okay? So final path will have the shortest distance. If the current sequence of operation is less than the final sequence, then this is the shortest path. Then this shortest path is updated to the shortest variable, shortest object. Right? Then the final is cleared, and this final will be updated by the new shortest path. Right? If not, if other case, if the current sequence of operation is greater than the longest, if it is more steps are there, if it is greater than longest, then this current sequence of operation is updated in the longest object. So this happens when it reaches a flag. Okay, when it reaches a flag, we give a reward 1. Okay, then we check whether the sequence of operation is for the first time, and if it is for the first time, we update the final dictionary, F dictionary, longest and shortest objects. If it is for subsequent paths, then we try to see whether the current path is shorter than the earlier stored path. If it is so, I update the shortest path. If the current path is longer than the longest path, then I update the longest path. Then the final destination is also modified here. If the next state is not a flag, in that case, if it is an obstacle, we go to this else part. Okay. So if the next state is not an obstacle, it can be any of this obstacle, obstacle 1, 3. So we have multiple obstacles in our environment. It can be any of this obstacle. In that case, we set a reward with -1. Okay, because it has encountered an obstacle, so we need to give a penalty. So we give a penalty of -1. So we say the episode has completed, so done is true, and we say the next state is obstacle. So our path, current sequence of operation, we don't want that. That is a wrong sequence of operation. So we clear the current path and the index value also initialized to 0. If not, if my next state is not a flag, if my next state is not an obstacle, it might reach an empty space. In that case, I set the reward to be 0 and say done is false. So we have not encountered any obstacle, we have not encountered any flag, so we say it as false. Next function is used for updating our environment. To refresh the environment, we just do a updation. Once our final route is determined, okay, so once the final route, so we get multiple paths, multiple sequence of operation to reach the destination. So from that we find the final route, which is the shortest path. So we try to see what is the shortest path using this function. So final function. So here we first delete the agent position in the environment. So we print the shortest path and the longest path. Then I am going to create some small ovals in our environment so that it shows the path of the robot movement in the shortest point. So we define some oval function. So I define the points for the oval and make it as a blue colored oval with completely filled, as well as the outline will be blue. So these points will be created, and using these points I am going to put the final path. Okay, so I am going to put the final path onto our environment. Okay, so the shortest path will be shown in our environment. Then that shortest path will also be going to our A variable, which has the shortest distance location. Next is, once we have got A, we can return that A. We can see the shortest path using this function. So now we have defined the functions. Now we are going to create an environment, right? So class environment. So we define the action space. We have 4 action space. One is up, down, left, and right. So up is formulated with 0, down is formulated with 1, left is 3, right is 2. Right? So we also determine the actions from the action space. What action? Whether up action has been taken or down action has been taken. So that action we try to determine. We put some title. So then we create an environment with a certain width and height. So height into pixels. So 9 into 40, which is 360. Again 360. 360 by 360, we try to create an environment. Then we try to define the dictionaries for storing the current sequence of operation. Then also a dictionary for storing the final path. Then the index is initialized to 0, and this C dictionary is used for whether we are updating the path for the first time or for the subsequent times. Since we are going to start our exploration, first we set it to true. Same way, longest and shortest is initialized to zeros. So we build the environment, reset, steps, update, as well as the final functions will be initialized in an environment. Now we create an environment. When we create an environment, you can visualize. So here you can see the environment. So with obstacles, an agent, and the destination flag. Right? So this is the environment. Now let us define a function for choosing an action. So in choosing an action, as I said, we use a parameter, greedy parameter, epsilon. Right? So I try to see the epsilon value, whether it is less than 90% or greater than 90%. Depending upon that, we will be making a Q-learning method, or it will be a SAS algorithm. So I generate a random number and try to see whether this random number generated is less than my epsilon. So usually the epsilon will be kept with the high value 0.9. So it can vary from 0 to 1. So we will be keeping it with 0.9 because more exploration can be incorporated. So we try to see whether my random number generated is less than epsilon. If it is so, we perform the action based upon the Q table content. Okay, we perform the action based upon the Q table content. Okay, so from Q table we take the observations, then using that we try to perform the action. If my random number generated is greater than epsilon, in that case we select the random action. Okay, we select the random action. Next one is the function for learning in the environment. So here what we do, first we check whether our next state exists in the Q table or not. Okay, we try to check whether our next state. So I perform some action. So the agent goes to the next state, whether the next state is available in the queue table. If it is available in the queue table, then I can select a value, appropriate action from the queue table. If it is not available, in that case, I have to add that state to the queue table. Right? So first we check whether the queue table is there for the next state. If it is there, okay, so we take the action and state. If the next state is not equal to goal or next state is not equal to an obstacle, in that case, we define Q target from the reward plus self gamma. Gamma is a discount parameter into self Q table dot location next state comma next action. So we get the Q target value. If it is an obstacle or a goal, in that case the reward will be assigned to the Q target. If it is a goal, then reward will be +1. If it is an obstacle, the reward will be -1. So this is for intermediate position. So based upon this, we compute the Q table entry for the state and the action. So with the help of a learning rate into Q target minus Q predict, we update the values in the Q table. So this process is called learning, which means the Q table updation. Q table updation takes place here. Next function which we use is for checking the next state, whether the next state is there or not. If the next state is available in the Q table, no problem. We can select the appropriate action. If it is not, in that case, we have to update that entry into the Q table. So that is what we do here. Check whether the next state exists. If not, we append it. We append the action and the corresponding state into the Q table. Next one is function for printing the Q table. Okay, so to print the Q table, so here I have the coordinates, okay, state coordinates. Then we have for up action what is the Q table entry, for down action what is the Q table entry, for right and left we have the Q table entry. So those things we try to print and see. So here we try to take a for loop. So using this for loop, the Q table entries will be printed. So then we try to print it and visualize. We can use a function to plot the results, like for each episode how many steps it has taken, right? So I can define plots for episode versus steps. For a first episode, how many steps it has taken. For the second episode, how many steps it has taken. So I can plot it and see. Same way for each episode, what is the cost function involved. So cost versus episode can also be plotted using this function. So now we create a function for Sarsa table, okay, Sarsa application. For Sarsa table, we need to give a parameter like learning rate is required, how frequently we need to update our Q table entry, and whether our Q table entry will be decayed if I have a wrong sequence of operation. Okay, if I have a wrong sequence of operation, then that results in a penalty, right? So this penalty can be increased so that the same steps can be avoided in the subsequent exploration, right? So the reward can be decayed. Okay, so if I perform certain sequence of operation, it does not result the agent to go to a destination. In that case, we can decay the reward. So thereby, I will not take that path in the near future. Then there is a epsilon parameter which enables for exploration. Okay. So we define the functions, learning rate, discount parameter, epsilon, and Q table entries. Okay, full Q table entry and the Q table entry only for the final path, final shortest path. So these things we have defined. So we have defined the functions also here. Choose action, learn, which is updating the Q table, check whether the next state is available in the Q table or not, print the Q table, plot the result. So these are the functions which we are going to use in our algorithm. Next is we try to update, right? So update our Q tables. So we take the steps. First we will put it as empty because right now we have not started, and cost also we have put it as empty. So observation, environment we try to reset. Then our recurrent reinforcement learning is going to take the observation. Depending upon that, the environment will be updated. So it will perform an action. Based upon the action, it will get the reward, right? And it will get the new observation. This is for next state and next action. So based upon the next state and next action, again an action can be determined, and using this a cost function can also be computed using this formula. Learning rate, action, rewards, we try to compute the cost function. Then we try to swap the next state with actions with the current state with actions. We try to update the values. Then we say one step we have taken, right? I see whether we have completed the steps or not. Like that we try to do it for each and every steps. So once it is done, we try to print the Q table entries for all the steps. For forward, up, what is the Q table entry? For down, what is the Q table entry? For left, right, for everything, we try to update the Q table entries. So finally, we come to this, our program. So we define a main function. In that, I create an environment, and we are going to run the SARSA table algorithm. In that, we give the actions, learning rate, decay function, and epsilon value. And we try to update the environment for every 100 milliseconds. For every 100 milliseconds, the environment will be updated. So this is going to run in a sequence. So when I execute this, you can see right now. So in environment, the agent traverses in different directions. Whenever it encounters an obstacle, it comes back to the initial position, and again it traverses. Once it reaches the destination also, it comes back to the initial position and it traverses. So like that, it will try to run in this unknown environment multiple number of times. So it will run about for 1000 episodes. For 1000 episodes, the robot is going to run. So then it will try to find all the path or all the sequence of operation which has resulted in reaching the destination. Then from that sequence of operation, it tries to find the shortest path, and it will try to give us the shortest path in our result. So let us wait for some time to get the shortest path. So it is trying to see all the possible combinations, all the possible shortest path, all the paths or the sequence of steps will be determined. Then from that it will try to find the shortest path. So now our algorithm has determined the shortest path of the agent starting from the 0, 0 position. So it has reached the destination. So this is the dots represent the shortest path of our agent reaching the destination. So here you can find that the shortest route contains 12 steps and the longest route, it contains about 6,670 steps. So these are the coordinates. So here you can visualize. So for shortest route, you can see the first coordinate is 0, 40. So 0, 40 means the width is 0, height is 40. So this one, right? So 0, 40, this one. This is 0, 0. This is 0, 40. Then after which it goes to 0, 80. So 0, 80 is, so 0, 80. Right? So you can take it as 0, 40, 80, 120, 160, 200. So like that it goes on. Same way 0, 40, 80, 120, like that it goes on. So the second one is 0, 80. Then comes 40, 80. This is 40, 80. So 40, 80. Next one is 80, 80. 80, 80. Then subsequent one is 80, 120. 80, 160, 80, 200, then 120, 200, then 160, 200, then 160, 240, then 200, 240, then finally 240, 240. So these are the 12 coordinates of the robot movement in our environment. If we see the Q table entries, okay, so Q table entries, you can see for each position. For each position, we have 4 values: Q, 0, 1, 2, and 3. So 0 is for up direction, down direction, left. 2 is for right, and 3 is for left. Right. So in this position, if I take up, it depends upon this Q value, right? So in this position, the robot will check whether I have to move in up direction, down direction, right, left direction. Which one it will choose? The maximum Q value. So the maximum Q value is this one, which is down direction, right? So what happens? It moves down. From this position, it moves down, right? So down as the highest value, so it moves down. So when it is in the 0, 80 coordinate, so 0, 80 is at this position, right? At this position, it will see which is the maximum value here. So if I see the maximum value, this one is the maximum value, 0.044636, which is 2. 2 is nothing but right direction. So it moves towards right. So like that, depending upon the Q table entry, the steps taken by the robot will be determined. So thereby the final path will be updated. Okay, so each and every step will be determined based upon the Q table entries. So if I see the total full Q table, it has 62 entries. So some of the portion is shown here. And finally, we also have an episode versus steps. For each episode, how many steps it has taken. You can see for certain episodes, more number of steps have been taken. For certain episodes, very less number of steps have been taken. Then for each episode, what is the cost function? Okay. If it has not reached the destination, then the cost will be more. If it has reached the destination, then the cost will be less. So thereby, we can see how our robot traverses in an unknown environment and how it determines the shortest path in an unknown environment. Once it finds all the possible combinations in the future, it can easily go to a destination by traversing the shortest path. So here in this tutorial, I have discussed about a reinforcement learning algorithm basics and how to use it for a robotic application. So thanks for watching. Please subscribe for more technical learning. Thank you.